Okay, so let's start with trees. I think everybody has joined. So tree is a collection of elements called nodes, which are um, okay. So what is a tree? So tree looks like this. So many times you have tree is a very common data structure. For example, the IITK. IITK can be visualized as a tree. IITK is the root. It has got various departments.
देखो फिर से स्टार्ट हो गया है। वो 6:30 बजे ही
Mm, I request everybody to get to mute themselves so that we can continue. Okay, so a tree is basically, so you already are familiar with the concept of node, right? A node means it contains the data, and also it can contain links to the next data points, right? So that is a node. A tree is a collection of nodes in which, so there is a hierarchical structure that every node has got children nodes. There are parents and children. So the topmost, or the one which is the parent of everybody, or kind of the super parent, that is the root. So the root is there, root has got the children, and then each of these children are parents of some other children. So this is a tree. There are nodes. One of them is called the root, and then there is a parent child relationship which makes a hierarchy on the nodes. So this structure is called a tree. So like IITK is there, it is the root, the parent of all, the root, and then it has got departments which are the children of the root. Then each department has got its own sub departments, and each sub department or stream could have got professors, right? Or it could have got uh, students, right? Okay. Now, one constraint in the tree is that every child can have only one parent. A child cannot have two parents. For example, if uh, this somebody Ram, he belongs to SPCOM as well as CA, so it cannot be, that cannot happen. A tree does not allow somebody to have two parents. Parent can have as many children, but children cannot have multiple parents. Children should have only, each child should have only one parent. Okay, that is the constraint on the tree. And tree is very efficient in many things which linear structures are not, right? So you see, this is non-linear structure. Okay, now let us see some terminology here. So you are familiar with the term node. Node means uh, one block containing data. Then you are familiar with the concept of root. Root is basically the topmost node which has no parent. So root has got no parent, right? And then the concept, the term parent, child, and sibling. So like there is one parent, it has got children, and this is a sibling of this. Like children are siblings of each other, right? Then the concept of ordered tree. If the tree follows a certain order, let's say the topmost has the is the largest, or the topmost is the smallest, and then there is some ordering to it. It's called an ordered tree. Uh, Path, ancestors, and dependents. So if there is a path means whenever there is a parent-child relationship, that means a path. So this is one path. So if I want to go from Hari to IITK, there is a path which exists. So Hari is child of SPCOM, SPCOM is child of EE, EE is child of IITK. So there is a path exists. But if I ask, there is a path from Hari to Ram, answer is no, because Hari is child of SPCOM, and so Hari and Ram, so basically ancestors and dependents. Ram is not an ancestor of Hari, and Hari is not an ancestor of Ram. So that is why there is no path. Path is defined basically in terms of parent-child relationship. So here it is there, but so it's unidirectional, you can say. From Hari, you can go to IITK, but it cannot come to Ram. So there is no path to Ram, but there's a path to IITK. So yeah, because the tree is directional, it is not undirectional graph. It's a directional graph. So in one direction only you can move. So ancestor means if I go parent, 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 am I able to reach this node? So then IITK is ancestor of Hari, but Ram is not an ancestor of Hari. Hari is a descendant of IITK, but Hari is not a descendant of Ram, right? Similarly, Hari is not a descendant of fluid mechanics or machining. Then the concept of height of a tree. What is the height of this tree? It is 4 number of levels in the tree. What is the depth of a node? So depth is measured with respect to the root. If the root is IITK, now what is the depth of SPCOM? Depth of SPCOM is 2, right? Now subtree. What is a subtree? So EE is a node, then this whole thing is one subtree of EE, and this whole thing is another subtree of E. Basically, look at each child along with the children of that child. So SPCOM is a child along with its children, that is one subtree. Then CA is another child of E. So CA along with its own children, that is another subtree. So these are subtrees of EE. So I hope this concept is clear. What is the concept of a subtree? So this was just some terminology. Now let us look at some uses or some implementations of tree. Okay, there is one very popular kind of tree. It's called a binary tree. Binary tree has at most 2 children, left child and right child. That is it. So basically each node for a binary tree will have these 3 entries. One is the data value. One is the data value itself. Like for this node, the data value is A. For this node, data value is B, right? Value. And then the link to the left child, a link to the right child. And if there are no, like let's say D, sorry, let's start from A. A has got my left child is this node, right child is this node. But let us look at this D. D has got, the value is D. Then for this node, the value is D. Left child is none, right child is none, right? So, okay, I think I did not discuss the concept of leaves. So the final nodes which have got no children, they are called leaves. So the nodes which have got no children, they are called leaves of the tree. So just like, when in the tree, the leaves, they don't have further, like a branch will have further leaves and many things connected, but leaf is a final end point. It has no further way to go. So that is why these are, when we have no children, they are the leaves. Okay, now let's come to a very, I think everything else until now, everything was very easy to understand, very simple, but now you have to pay some attention. Now we are doing tree traversal. So now it is, for example, if you have a linear structure and I ask you, can you please search something here? Let us say you saw the stack of red and blue and yellow plates. And I ask you, okay, does this stack contain a yellow plate? Does it contain a red plate? What will you do? You will traverse the whole stack and check each and every entry. Traversal means checking each and every entry. If it is a linear data structure, then traversing is very easy. It's an ordered traversal, right? But tree is not a linear thing. So how do you traverse the tree? There can be different approaches. And so there are 3 popular ways for traversing this nonlinear ADT called the tree. What are these? The first is the pre-order, in-order, and post-order. So what is pre-order traversal? So I have drawn here this tree, which has got N is the node, let's say the root node, and it has got subtrees T1, T2, Tk up to Tk. So what is the meaning of subtree? It means the child of N along with its children. the child of all the children of n along with their own subchildren, they form different subtrees. Now I can traverse this tree in pre-order fashion if I visit node n first, then I visit T1, followed by, then I visit T1 also in pre-order. Now see, this is a recursive traversal, right? Because in the function pre-order, I am calling pre-order again. And this is converging towards, termination. How? Because this tree is smaller than the whole tree, right? I'm breaking down the bigger tree into smaller tree. So it is converging towards uh, terminating case. So what I do is, okay, I visit this node first, the n node first, then I do a pre-order traversal on T1, then a pre-order traversal on T2, then a pre-order traversal on T3, so on up to Tk. This is called pre-order traversal. I visit n, then T1, T2, Tk. Now, another fashion could be in-order traversal. In the in-order traversal, I visit T1 in order fashion, then n, then T2, then others, and in the in-order fashion. So this is also a recursive traversal, right? In the function in order, I'm calling in order again, but on a smaller tree, this subtree of the subtree T1. So this is in order traversal. Similarly, post order traversal means I visit T1 in a post order way, T2 in a post order way, so on up to Tk in a post order way, followed by n, right? So basically, to mnemonic to remember is, if n is visited first, it is pre-order. If n is visited in the middle, it is in order. If n is at the end, then it is post order. Okay, now I know things are not clear until now. Let us do an example. So I have replaced my subtrees and n with the concrete nodes, a very simple tree. It has got a parent A and it has got two children B and C. B and C are the leaves and they don't have any further children. So pre-order traversal means what? You visit the n followed by all the subtrees. So I visit A, right? Then I do a pre-order traversal of this subtree. What is the meaning of pre-order traversal? I will write down, I visit this node first and then the subtrees of this node. And this has got no further children, no subtrees. So that is why this is terminated. The terminating case has been achieved. Now go to the next subtree, which is this subtree. This also has got no children, so only C. So the order is A, B, C. This is in this order, I will visit my nodes A, B, C. So now if I ask you, is there a node containing C in this tree? Then you will visit this. No, no, yes, I found the node C. I hope the idea is clear. Now,
if there is children of B, then we will visit first children of B or C.
Good question. In the next example, we'll see that. Okay, good question. Okay, now the next is in order traversal. What is the meaning of in order? The root node is in the middle. So first I will visit the left subtree. The left subtree is, I will visit only single node B, then A, then C. And in post order, I will visit B, then C, and the root will be at the end in the post order. B, C, and then A. Okay, so now as you asked, what is tree traversal when there are children of B, C also? Okay, let us go step by step. In the pre-order traversal, I'll visit A. Okay, I am visiting A, followed by left subtree, followed by right subtree, right? So I'm visiting, first I'm visiting A, right? So this part is done. This is over. Now I have to do a pre-order traversal of this tree, this subtree. So what is the order? I will visit B, then I will visit the subtree, left subtree, then the right subtree. So, okay, B is also done, right? And then left subtree, this is D, this is E. Basically, you already know how to traverse this subtree, B, D, E. So the B, D, E is there. So this subtree is traversed in this way. Now come to this subtree, C, F, G. C, F, G. This is the pre-order traversal. So in this way, you have traversed the whole tree. So let us look at this again. So the order is A, B, D, E, then C, F, G. This is the pre-order traversal. So it is also called depth first traversal or depth first. Why depth first? Because you starting from A, B, D, you're going to the deepest point here, D, then going to the next deepest point, then starting from the other branch, going to the deepest. So it's kind of a depth first traversal. Okay. Now, next is in order traversal. In the in order traversal, what is the order? First left subtree, then the root node, then the right subtree, right? Okay. So let me write it down. So let me see. I hope this thing will work properly now. Okay. Now we are doing in order traversal. In the in order traversal, I will do, it is first in order of this BDE, followed by A, followed by the in order traversal of CFG. I'm drawing it in short. This is not a standard notation, just for explaining, I'm doing it this way. Okay, now what is the in order traversal of BDE? It is DBE, right? You've already seen DBE. So I will write here DBE and then A and then here FCG. This is the in order traversal. That's what I have written here, right? Now come to the post order traversal. Let me use a different pen for this. Maybe light blue. So what is a post order traversal? So you visit this tree first. So this will be the post order traversal of BDE, followed by the post order traversal of CFG, followed by the node A, right? Now, what is the post order traversal of BDE? This is DEB, right? So DEB, like DE followed by the root node, comma, post order traversal of this. So this is FGC, followed by the node A, right? DEB, FGC, followed by A. So this is the post order traversal of this tree. These three schemes are common. Okay, anybody has any questions, write on the chat window. Okay, let's go to another example. You can do it yourself. This is not a binary tree. Now multiple subtrees are there. So pre-order of one is like a depth first. 1, 2, then 3, 5, 8, then 9, then 6, 10, then 4, 7. Depth first kind of traversal, pre-order traversal. And in the in-order traversal, you follow the order. You make an arch, basically. An arch, 2, 1, then 2, 1, and then you start from here. 8, 5, 9, then 3, then 10, 6, then here 7, 4, right? Okay, let me tell you the arch concept here first. Okay, you do an arch, basically DBE, then A, then FCG. So you make an arch. Means it is okay. Just for I think once I discuss heaps, then it will be very clear the utility of in order traversal. Okay, you have to wait a bit for heaps to start. we have only 15 minutes left. Let's see how much we can do in today's session. Okay, this is the tree. Now writing the codes. Okay, for pre-order traversal, I have a function called pre-order traversal, and the input is the root node. Now remember, this root node contains the pointers to the next node. So basically, if I tell you the root node, you can reach the other nodes, right? The reachability is there. Okay, so I'm giving the root node as the input to this function. It's a recursive traversal, recursive function, right? Because so what does it do? It will visit the this root node only first. It's printing the root dot. Let us say I'm just printing the values. I'm not comparing. It is traversal in which I'm just printing out the values. So I print this value, right? And then I do a pre-order traversal of left node. Then I do a pre-order traversal of the right node, because node also contains the tree within it, right? Because node has the pointers. So pre-order traversal of this node and pre-order traversal of this node. So, and if the node is none, basically if you reach the leaf and after the leaf the child is none, then you return. Means you don't need to print anything, your function is over. So you are converging, right? Your terminating condition is this. So this is your terminating condition. Always put your terminating condition at the top and then the recursive cases. So I think this is very clear.
So in order, you're going to the topmost, the root after second. It can be, I mean, you can go after third also.
Okay, no, it's a convention that you always do first subtree, then the node, then the all other subtrees. It's a convention. Good question. Yeah. Okay, so next comes the in order traversal. It's again a recursive thing, right? The function calls itself. Okay, now Ali has a question, very good question. I will come to this question after explaining this. I will after completing this. So in order, the terminating condition is okay. If the node is none, basically, then you return none. That is you terminate the function. And then this is first you do in order traversal of the left node, then the current node, then the right node, right? And similarly in the post order, the terminating condition, and then post order traversal of the left node, post order traversal of the right node, followed by the current node, right? Left node, right node, and the current node. Okay. These are three kinds of traversals which are possible. Okay, so Ali has a question that what is the application of such traversal? I gave one application that, let's say in the search, when you are searching for something, you have to go to each node and check whether your value is there or not, right? So that is a very useful application of pre-order and post-order traversal, basically when you are finding your solutions. You will see many interesting problems and in which this traversal, like I told you, okay, two common approaches for searching for solutions is one is called depth first search, other is called the breadth first search. In the depth first search, you basically do a pre-order traversal, that you go to the deepest point 1 2 then 3 5 8 then 9 6 10 then 4 7, depth first search. You're searching for something and you are going to the deepest point and then going to the next branch, going to deepest point, next branch, deepest point. So that is one way of searching on the tree. Another is breadth first, where you do 1 2 3 4 5 6 7 8 9 10, like doing level by level. That is another way of traversal which is not discussed in these three popular types. Okay, so the application is just that the most popular application is in search. When you are searching for something, you have to visit each and every node. So Manoj has a question. I'm unable to understand how data is stored here. I gave you an example. Where was it? It was here. So how the data is stored? Data is stored here. The value is stored in the node. So each node is a class, or it is a structure right? Each node is a class and it contains links to, so node is a class and it has got instances. So for example, I will create, let us say I want to create this tree. How will I create this tree? I will say using this class, I will say first my, okay, let us say my root is equal to node. I have to give value first. Value is a, comma, left node. Left node is, okay, let it be none for the time being. Now I create a new node. Okay, let me say root dot left is equal to node B, right? Root dot left is the node B. Now I'll say, now B has a child D. So I will say root dot left is equal to node D. In this way I can create, right? So this dot left gives me a handle to the lowest and lowest levels. Okay. And I can also do it in a function, let's say using a for loop. I will create a dummy pointer to this. Means, okay, I think you will understand these things once you do exercises or do some examples on this, right? And this is how the data is stored. The data is this A, B, C, D, E, F, G. This is our data. Okay. We have 10 more minutes to go. Let's see what is the next topic. Okay, this part is clear. Okay, pre-order traversal we have already done. Any other questions you have?
Sir, tree can store heterogeneous data?
Yeah, why not? You can give heterogeneous data, meaning strings in some nodes, integers in some other nodes, floats in some other nodes. No problem. It depends on your implementation. Like in this implementation, which I have written, it has got no restriction on the value. Value could be a string, it could be a number, it could be float, anything. Or it could be an array, doesn't matter. It could be anything. I have no restriction here. Okay, now let's come to the another kind of tree. It's called a binary search tree. Okay, so a binary search tree is a tree. It's a binary tree. What is the meaning of binary tree? I think we have seen before. Okay, binary tree. Yeah, we have seen it before. Binary tree means it has got only two children, left child and right child. That's it. It at most it could be left child could be none, right child could be none, but at most two children are possible for a binary tree. Now, what is the meaning of this term search? What is a binary search tree? Binary search tree. Another condition is imposed on this tree. The condition is that the left subtree has all elements which are smaller than the node, and the right subtree has all the elements which are larger than the node, provided there are no repetitions of elements. If there are repetitions, then it will become smaller or equal to, or larger or equal to. But assuming there are no repetitions, it is smaller and larger. So this part is all smaller than 5. This part is all larger than 5. See this, my root node is 5. This subtree has got entries 1, 2, 3. They're all smaller than 5. This subtree has got the entries 6, 7, 8, 10. They are all larger than 5. And this property will be valid for every node, not just the root node. If you go to this node, see the left subtree is 1, which is smaller than 2. And the right subtree has only 3, which is larger than 2. And at this also, what is the left subtree? Left subtree is none. That is all right. And the right subtree has got 7, 8, and 10, which are all larger than 6. So this is following the BST invariant property. binary search tree invariant. Now go to this node. This node again follows that property. The left subtree has 7, which is smaller than 8. Right subtree has got 10, which is larger than 8. Okay, so this tree satisfies the property of BST invariant. Now tell me, what will be the in order traversal of this tree? Do an write on the chat window, write in order traversal for this tree. Could you write? How will the in order traversal look like? Yeah, I think you got it. Yes, so it will be 1, 2, 3, 5, 6, 7, 8, 10. Like I told you, right, making arches. So you can see now, you can get the idea that how in order traversal gives you the ordered list of numbers in a binary search tree. So in this tree, you cannot have heterogeneous data, right? Because we have to compare the data. The data on each node has to be comparable. So that we can define a larger and smaller notion of large and small. Basically, it has to be comparable, right? That is why it is this subtree does not allow heterogeneous data. Okay. Now, what is the advantage of binary search tree? The advantage of binary search tree is that the insertion, deletion, search operations are very fast. Now, I will give you a quick example. Can you find the number 3 in this tree? What will you do? So instead of checking all the entries, or let us say try to find 10, right? If you do in order traversal 1, 2, 3, 5, 6, 7, 8, 10, the search is of order n, right? Order n, which is a very bad search, but there is an efficient method to search a binary search tree. What is that method? I go to the top root node 10. Now I know 10 is larger than 5, so it cannot be there in the left subtree. So I go to the right subtree and I'm here at 6. Now I know 10 is larger than 6, so it cannot be there in the left subtree of 6. I have no need to traverse that tree. I skip that traversal. I go to 8 and to this node, to the right subtree. And here in the right subtree, the entry is 8. I know 10 is larger than 8. It again cannot be in the left subtree. I'll go to the right subtree and I found a 10 there, right? So you see, instead of doing 1, 2, 3, 4, 5, 6, 7, 8, instead of doing 8 search, instead of checking 8 nodes, I have checked only 4 nodes and I have found my answer. So that is an illustration of how binary search tree is helpful in searching for data. So in general, if I construct my binary search tree properly, then the search operations are very fast. If it is a poorly constructed tree, basically, imagine if I construct a tree like this. If I make a tree 1, 2, 3, 6, 8, 10. The question is it a BST? Is this a BST?
Yes, sir.
Yes, because it follows that property that left subtree has smaller entries than there is no left subtree. So this means the right subtree has all larger entries. So this is a BST, but this is a very poorly constructed BST because again, it is like a linear thing. If I have to find 10, then I have to go through all the nodes, right? So I can rearrange this tree so that the length becomes small and then it will give me the speed up, right? So not every BST is efficient, only when it is balanced or when it is the minimum depth. That means when you reduce the depth, you make it balanced that left subtree and right subtree are almost same length, same size, then it gives you the speed up. Okay, we will study this in much more details later, but I think this makes you aware, like this gives you a fairly good introduction to the binary search tree. I think we can stop here. It's almost 6:30 now. If you have any questions, please ask. And in the next lecture, we will move on to the next topic, which is very similar to what we just discussed today, the topic of heaps. Is there any questions? Then please ask.
So in the binary tree, uh, when we write a program, we can define dot left and dot right. But if it's a general tree, there can be as many children, so it has to be dynamic. How that could be implemented?
Okay, good question. So based on the today's lecture and the yesterday's earlier lecture, can somebody suggest the answer for this question? If it is not a binary tree, it is general tree where every node can have any number of children. So how will we implement it? Let's say in this, no, not in this, in this class, we have a class node. I'm writing it not for the binary tree, but for any general tree. What will be the entries in my class? Yes, so Richie gives a good answer. He says maintain a list of pointers to the children. So in that case, my children will not be just left and right. It will be a list. It could be a linked list. It could be a like Python list, right? So basically a list. So good answer from Richik and Saksham. Thank you. Yeah, so you have the value and you have the self.children, and the children is a list which contains links to all the child nodes. Okay, any other question? Okay, if not, then we can stop here and see you in the next class on Monday. Thank you very much.
So actually, instead of maintaining a list of pointers, all the children could just point to the parent.
Okay, see, we are making it a directed graph, okay, directed tree or directed graph, where you only means if you see here, you are only storing the root node, right? And from the root node, you are moving to access every other node, right?
Okay.
You start from the root node and move on to every other node. Your starting point is the root node. So if you have a pointer from child to the parent, then starting from the root node, you cannot reach there, right? Because it's a singly connected or a directed graph.
Yes, sir. Okay.
Yeah. So tree is a directed graph. So we always have the root node, and from there we want to visit everything else.
Okay, sir. Got it. Thank you.
And also, okay, another point here. If we have one child, it can have only single parent. So you will not know whether it is a binary tree or what kind of tree. Means you have to see how many children have this same parent. So means okay, many properties will be difficult to analyze in that case. Of course, it will bring some simplifications, but many complications as well. Okay, thank you. So good question, and I think we can stop here. Thank you.